and I'm going to introduce you to our team today. So my name's Rachel Mills, and I'm the head of Ocean and Earth Science, and I'm one of the educators on the Exploring Our Oceans MOOC. And here to my right is Millie Watts. Millie Watts is one of the mentors on the MOOC that you have met on the forum. And to her right is Simon Boxall. Simon is one of our admissions tutors for Ocean and Earth Science here. He's got a lot of experience of UCAS admissions procedures, and he's going to answer questions about oceanography and UCAS later on. To Simon's right is Amelia Astley. Amelia is one of our PhD students in her third year of her PhD. She's actually been facilitating a different MOOC in submerged worlds, but the reason why we've got her here today is she studied as an undergraduate in terms of the oceanography program, which we offer here. And then to Amelia's right, we have Derek Keir. Derek's another one of the admissions tutors to answer questions about geophysics and about admissions procedures in general. So we've got a lot of questions compiled from week 2 of the MOOC that have been actively discussed this week, which we thought we'd start by discussing. And then we thought we'd spend the latter part of the Google Hangout talking about UCAS process and how you might apply for degrees here in Southampton and try and answer some of those questions. Okay, so we've printed off a lot of the questions from the forum, and really I'm just going to go through these and hand them over to my colleagues for them to answer. So the first question I've downloaded is a question from Leslie Hamilton. And Leslie says, what I don't fully understand about this bulge theory is that it would imply there is a high tide at the same time in one geographical area. However, on reading the article on why the Isle of Wight has 4 tides a day, part of the explanation says that there is a high water at Dover at the same time as low water at Land's End. Wouldn't the bulge of water affect the whole of the English Channel at the same time? Or is it that the sloshing about of water in the oceans is really much more influenced by depth and coastline shape? So that's a great question, and I'm going to pass that over to Simon.
Thank you. The first reason is, why do we get bulges in our tides? Well, it's a balancing. If we forget tide altogether and we start off with the moon and the earth, the moon's going around the earth, and there are 2 forces. There's a gravitational force pulling the moon and the earth together. But also there's a sort of it's a centrifugal acceleration. And I won't get into arguments about centrifugal versus centripetal, but it's an acceleration wanting the Earth to move, or the Moon to move away from the Earth as it spins around. And they're in balance. If they weren't in balance, then either the Moon would crash into us or it would disappear off into space. And that hasn't happened. So at the center of the Moon, the center of the Earth, these 2 forces are in balance. Now, if we go to the lunar side of the Earth, then their gravitational pull towards the Moon is stronger than this sort of centrifugal acceleration. On the far side of the Earth, the gravitational pull is weaker than the centrifugal acceleration. The radius is bigger between the Moon and the Earth, so it's a bigger force going the other way. And so we end up with 2 bulges. On one side, it's because the gravity is bigger than the centrifugal force. On the other side, it's because the gravity is less than centrifugal force. And as the Moon goes around the Earth, so we get this wave of water moving around the planet. Now, why do we then get 4 tides in Southampton or along the Isle of Wight? The reason for that is to do with the way in which the wave moves. In a perfect world, the water would just move around the Earth, or rather more correctly, the Earth moves in the water. And in a perfect world, if the water was deep enough, it's about 22 kilometers, it wouldn't slow down because of friction with the seabed. Because it is affected by the seabed friction, it slows down. Now, as our wave enters the channel, it comes as a single wave up the channel. But if you look at the depth across the channel, on the English coast, there's a long shelf. You've got things like Christchurch Bay, Poole Bay, Weymouth Bay, and these are shallow water shelves that go out to the water in the middle of the channel. On the French side, it's much deeper. And so our wave comes in, it's like a train splitting. The fast train continues up the channel, in the middle of the channel on the French coast. And that wave then hits, for example, the Isle of Wight very quickly. But because it splits, the slow wave is working its way around the coast. And so that means that this second wave appears about 2 hours after the first wave. And that's why we get a double high water. It's because the wave is split, the fast train gets there before the slow train, we get 2 waves. Hopefully that explains why we get 4 tides a day at the Isle of Wight. Of course, this happens twice because eventually, as we go round, the other wave appears the other side.
Thanks, Simon. That's a really clear explanation, actually. So let's move on to another question Second question I've got is from Margaret Gobby. And Margaret says, which places exactly sometimes only have one tide a day? Is it a place on the equator, or is it at very high latitudes, or both? Or is it somewhere else entirely? So I think I'm going to pass that to Amelia.
Hi. So this is to do with the fact that the orbital plane of the moon is not exactly above the equator of the Earth. So if you imagine the Earth, then you have the moon is slightly offset. Therefore, as Simon was just saying, the bulge, which if the moon was perfectly rotated around the equator, would be at the equator, is slightly offset too. So therefore, at the higher latitudes, where you have the bulge rotating around, it only goes over once a day, so you get diurnal tides. So places such as the east coast of Russia and Alaska and Antarctica have diurnal, or one tide a day. However, this again is following that kind of perfect scenario where there's no land masses and where the oceans are a certain depth. However, in real life, we have land masses and depth variations as well. So there are other locations which are in fact on the equator. So in some locations in the Gulf of Mexico, where we also get these diurnal tides. So hopefully that's answered your question.
Thank you, that's great. Let's move on to something a bit more geophysicsy, because we've got Derek here. And we have a question here from Stephen Savage. And Stephen says, I was interested by the article, Has the Earth Gained or Lost Water? However, it mentions that Venus and Mars lost their atmosphere because they lost their magnetic field. I found this interesting, but when I looked for other articles, some of these said that we don't know if this was the case with these other planets, and it certainly makes sense that the magnetic field helps protect our atmosphere and water. So Derek, do you want to comment on that?
So this is it's a very good question and kind of a hot topic in planetary science. So it is true that the presence of a magnetic field helps to protect our atmosphere because it deflects the highly charged solar wind, which, if the magnetic field wasn't present, would strip away the light gas particles in the atmosphere. Another important factor generically for maintaining an atmosphere is having a planet with large enough mass and a large enough gravitational field. So both of these factors interplay to maintain the atmosphere. So for example, in the example of Mars, the magnetic field stopped around about 4 billion years ago, and because the planet is very small, the gravitational field couldn't maintain the atmosphere alone, and so it was stripped by the solar wind. Venus is a different example, actually. It does have an atmosphere, even though it doesn't have a magnetic field. And this is because the mass of the planet alone helps to maintain the gas particles in the atmosphere. And also in combination with that, because an atmosphere is maintained, the solar wind interacts with the atmosphere to create a charged layer around the outside of the atmosphere, which functions to deflect a portion of the solar wind. So that also helps to maintain the atmosphere. On Earth, we have both a planet with a reasonable mass and a reasonable gravitational field, which maintains the atmosphere, and we also have a magnetic field, which kind of provides additional protection.
Can I follow up with a question? How do we know that Mars had a magnetic field that stopped 4 billion years ago?
I'm not sure exactly. We do know that the magnetic field on Earth is created because we have a liquid outer core. In Mars, we don't think that it does. I'm not sure exactly how we know that it ever did have a magnetic field to start with.
Sorry. I'm going to move on here to another question from David Williams. David's actually given us a couple of questions. We're going to start with the second one, and I'm going to address this to Millie. What about the opposite of the ice caps melting? In some past ages, water was taken out of the oceans as ice. This then exposed the Gibraltar Sill, cutting off the Mediterranean from the Atlantic. The Mediterranean waters then evaporated, leaving a bed of salt. So, Millie, would you like to comment on that?
Yeah, so this is a great question. We do know that the level of the ocean has actually fluctuated by about 120 meters as we go from ice ages to interglacials, and we're presently in an interglacial. But that does mean that when the ice caps have been larger and they've started to grow, the global sea level is as much as 120 meters lower. The Mediterranean is a really interesting example of what happens during these periods. So about 5.93 million years ago, we know that sea level fell and the Mediterranean became an enclosed basin. And it's the start of the time period that we call the Messinian salinity crisis. And during that period of time, a combination of tectonics, so the soil being uplifted, a mountain building taking place on either side, in addition to lower sea levels, means that the seawater that was within the Mediterranean evaporated slowly, and it's actually left behind almost a kilometre thick of evaporite deposits, which are particularly important for us. We've got gypsum there that makes its way into cement, as well as things like toothpaste, makeup, talcum powder. You'll find the gypsum from that part of the world in almost every type of cosmetic you can buy here. And this is actually one of our locations for our second year geology field trip. It's very classic geology, and we go and we explore what those sequences look like over a 2-week trip to the south of Spain.
We can talk more about field trips.
We can.
That sounds great. Okay, let's go to David's other question then, and I think maybe Simon can go answering this. So David's other question was, what input does the thermal gradient between the warm western currents at the equator and the cold polar regions have on the velocity of these western currents? The laws of thermodynamics would indicate that the warm western currents would be driven down the thermal gradient that exists between the equator and the pole region to lose energy and attain equilibrium. So again, do you want to comment on that?
That's a very complex, a very good question, a very complex one. The oceans and the atmosphere, first of all, are very closely linked. So the oceans, in some ways, drive the atmosphere. They drive these sort of cells of circulation, Aggie cells of the atmosphere. But they in turn drive the surface circulation. And so when we look at the ocean currents, particularly the surface ocean currents, what we're looking at is this balance between the warm and cold areas, if you like, the high pressure, low pressure areas of the oceans. And the same as the atmosphere, water tries to flow between high and low pressure, and as it does so, it's deflected by Coriolis force, creating these circles. But it's further moderated by the winds as well. Now there's another complication, and that is in the high Arctic, as ice forms, the ice itself creates very saline water masses. Sea ice is actually pretty much fresh water, and it squeezes the salt out. And as that happens, the salt water sinks quite rapidly. It's a bit like taking the plug out of the bath. When you do that, the surface water is drawn across towards that sinking mass. And we end up with what we call the sort of the overturning, the thermohaline circulation of the oceans. And so we get this conveyor, the Atlantic conveyor, where water sinks at the poles, heads towards the equator again, and the surface water is also drawn towards that sinking hole. So you've got this combination of winds, you've got this thermal gradient in the oceans, which does drive, as you say, the water masses, but also this sinking effect, which is drawing surface water. This is why it's very difficult to predict what would happen if. What would happen if we warm our oceans up by a small amount? What would happen if we stopped ice formation in the Arctic? What happens if our wind patterns change as we see the jet stream, for example, becoming more meandering? We're getting more meanders in the jet stream at the moment, which explains some of the weather we've had in 2014. But also the jet stream has suddenly started moving further south. These cells are changing their structure. And it's such a complex picture, we don't know the answer. We don't know exactly what the pattern of circulation will be, say, in 50 years or 100 years' time. And these are the big questions people are asking now in climate change. It's not, is it going to happen? It's, what's it going to look like? So it's a good question. We don't really have the full answer.
And the next question, I think, leads on from that, and that I'm going to, this is from Carrie Weinhold. Carrie says, just curious, how exactly are we able to track the cycle of water, which takes about 1,000 years? Even if we know the movement of currents through the world, how do you know exactly what path the radionuclides that are absorbed into the surface waters that we use to track the ocean circulation, how do we know what path they take through the ocean? Once these surface waters hit deep currents, it's clear as to where they will travel, and how do we know that? So again, let's start with Simon, and maybe Millie can comment.
Gosh, okay. One of the radionuclides we use is brainstorm.
Carbon-14.
Carbon-14.
There you go.
Well, there are two, actually. We can use tritium, which was released during the 1950s when we started playing with hydrogen bombs. And tritium is one good short-term tracer because the only source of tritium on the planet is from what we did. And it's in the atmosphere, and the only way it can get into the ocean is through the ocean-atmosphere interface. And so for short-term, over, say, a period of 40, 50 years, we can look at tritium levels And if water in the deep ocean has tritium in it, we know that water has been near the surface. So that's one technique. We can also use carbon-14. We can look at the relative components of carbon-14 to carbon-12 to again work out a rough age. It's quite a coarse grading of the age of the ocean water masses, but we can use isotopic analysis. And of course, with recent developments in places like Fukushima, where we saw radioactive iodine and other nuclear radionuclides being released, we can actually trace those radionuclides. I suppose if there's a spin-off, the terrible thing was the fact that there's a huge tsunami and that there was a terrible disaster in the Fukushima plant. The only benefit to science is we can actually trace that material and understand a bit about, for example, the Pacific circulation. It's a very small spin-off, but it's one thing we are looking at as science.
Do you want to add to that?
I think I'll just add it's one of the key areas of development in sedimentology and paleoceanography at the moment, that when we look at water masses and sediment, you have to account for how old that water is, and we often don't know for different parts of the world. So there are estimates that in the Arctic during the last glacial period, the waters were actually there for 1,000 years, whereas maybe they're only 300 to 400 years old now. And there's a lot of ongoing research into how that works and what that means for interpreting our paleoceanographic database.
Thank you. That's good. Let's have a little bit of a chat about one of the really more contentious topics on the forum. Let's talk about tidal barrages, because I think there's been a lot of discussion from the learners out there on our forum, and we've got a question here from David Stanning. So David starts by saying, I've never understood why we haven't tried harder to harness the undoubted potential energy source from tides in the Bristol Channel and the Severn Estuary. It surely can't be the persuasive power of conservationists. With turbine technology improving rapidly, this tidal source of energy should no longer be ignored. Far more efficient, I suspect, than the currently unreliable and inefficient wind farms that plague our horizons. It's quite a contentious comment there. Again, I think we should all want to go at this. Who would like to say something about tidal barrages and capturing tidal energy and the Severn Estuary in particular as a location for us?
Well, I'm from Somerset, and it's certainly a particularly hot topic there. I have to say I'm in favour of harnessing the energy, though I'm not in favour of the traditional approach to just putting a barrage straight across the Severn. There are alternatives to that, however, and I mean this plan has been in the works since the late 1960s, and it looks like at the moment we might have reached a nice compromise, which Simon can probably talk a little bit more about.
Yeah, I mean, there are two reasons why the Severn barrage hasn't gone ahead. There are some concerns in terms of the environment and the fact that it will change the environment of the Severn and the Severn Estuary quite dramatically. But there are also concerns because the mechanics of building a barrage across the Bristol Channel is significant, and you've got to look at this cost versus benefit. And I think a lot of engineers looked at the problem and decided that the costs were too high. What has happened is, first of all, there's a network of tidal lagoons, those small-scale barrages, if you like, that are being developed along the Severn Estuary. The Severn Estuary is ideal because it has a huge tidal range. In fact, at the top of the Severn, you've got a 15-metre tidal range. So it provides lots of energy. And they are actually in the final planning stages now for the first of these barrages, or lagoons, which will go ahead off the coast of Swansea. This lagoon will provide enough energy to power all the domestic requirements of Swansea and the region around Swansea. It'll power something like 30,000 homes. And it's the smallest of 5 planned systems. And they're going to start building at the beginning of 2015, so it's imminent. At the same time, there are turbines going in rather than a barrage. The advantage of a lagoon is that you can control when and how the water is released. So you can hold water back for that peak at, say, EastEnders break or something like that when the power is needed. But they're also they've started putting in a series of single turbines, a bit like wind farms upside down, in the area off Pembroke and also off the Scottish Islands. Those are due to start putting energy into the grid very soon, in the next few months. So these are happening. They haven't had a very high profile. They don't create the same sort of emotion as wind farms. And I'd be very careful. wind farms have a place, particularly the offshore ones. They are more reliable than people imply. There's a lot of myth and legend about wind farms, and they do provide a significant amount of energy. And some of the big companies, people like EDF, are investing in these things. They have a commercial requirement. They're not going to invest in these things if they're not going to provide money. So they do work. If they didn't, they wouldn't build them. You know, we don't do it for fun. So it's a combination. You need this combination of wind, wave, tide in order to provide the energy we need for the next few years.
The largest wind farms currently being built for the coast of England. And they're normally so far away from the coast that you can't really see them. So they don't really create a significant eyesore for the public. So the UK is investing heavily in wind energy at the moment. And I guess in the long term, with the addition of tidal power, will be kind of well placed in terms of renewable energy.
I think one of the other considerations that should be put in place is also the damage that might be done to archaeological resources as well, because especially along riverine areas, then there are no paleo landscapes. So these are areas where we once inhabited when sea levels were a bit lower and now are submerged. And these have amazing potential to preserve our archaeological material. And so that's another important aspect of the planning of these structures. And the advantage of the sort of more turbine type structures is that if a location is deemed to have archaeological potential, then we can always put it in elsewhere where there might be less of a chance of destroying some of our archaeological heritage.
But I think you've got to look at a balance. I mean, people will always argue whatever you do will have an impact of some sort on the archaeology, on the marine life, on the terrestrial life. And it's a balance really of, you know, do you have the risk that maybe a few birds will fly into a turbine, or maybe a few fish may be affected by submarine turbines? You've got to balance that against the impact of fossil fuels, the effects of climate change, which is enormous. You know, we're going to get sea level rises, which will make the effect of tidal lagoons look pretty small. Nuclear power, there are lots of pros and cons on that. If it works well, it's perfect. When it goes wrong, it's a catastrophe. So you've got to look at the alternatives. The only way you don't have an impact is by turning all the lights off. And I can't see people on the planet today deciding, that's it, we'll turn the lights off, we'll turn the computers off. This is the last Google broadcast we'll do, no more power. We need power, and we need to find the least disruptive way of generating it.
Thank you, Simon. The next question, and probably the last one we'll take from the forum, relates to that, and this is from Sandra Morgan. So Sandra says, I found the explanations of the gyres and the forces involved very interesting, which is good, but in the light of previous discussions around the tidal barrage, I was wondering whether using energy from the oceans could affect the ocean system itself. For example, if many countries all over the globe circulation or other impacts in the ocean. So, should we comment on that?
No, is the short answer. People have looked at this as a sort of what if, and it's a sort of question that politicians often ask, because, you know, please slow the moon down. Scientists have done a calculation, and they worked out that by extracting the energy through tidal power, if we had the most efficient tidal power extraction system, then we will slow the moon down. It would actually be like by about a second every million years. I'm not worried about that. And actually, there are more fluctuations than that anyway in the natural cycle of the moon, and also, of course, the Earth around the sun. Remember, tides are created not only just by the moon going around the Earth, but also by the Earth going around the sun. So there is an impact. You can calculate it, and it works out at about a second every million years. It's not going to affect us.
That's a good answer. I think I want to move the discussion on now, because I know we've got a lot of people out there that are interested in applying for degrees in science all over the country. And I think we've got two of our admissions tutors here, so we've got a chance to actually answer some questions about how do you apply to university, what sort of degrees do we offer, we could talk about the field work that we do. And again, we've compiled a list of questions that have come in by various sources. We have lots of our UCAS applicants actually just email us directly and ask us questions, which we're really happy to answer at any time. And then we've had questions coming in via Twitter and questions coming in via the forum. So let's start at the top of the list, shall we? And say, one of the things we do with here in Ocean and Earth Science is we invite all applicants who are interested in bringing to the university for an interview Everybody comes for a day where they spend time understanding, learning about the department, learning about the courses we offer, and then we have a one-on-one interview and discussion with a member of academic staff. Now that's obviously a little bit, stressful. It's a little bit scary, but it's actually a really important part of the process in terms of having a discussion with an academic about the detail of the program we applied for. So we get lots of questions around what should I expect from that interview and that presentation I'm asked to give. So Derek, do you want to try and answer that from your perspective?
Yeah.
And then we'll come over here.
So I'm the geophysics admissions tutor, and at least in the geology and geophysics interview, the interviews last around about 25 minutes or so. And the kind of main aim is, one of them is for us to gauge the student's interest in the subject. So the questions revolve around why the applicant's interested in studying geophysics in general, and then secondly, why they're particularly interested in coming to Southampton. And then likewise, the student also can ask the interviewer any questions they have about the degree program and the university. In terms of the presentation, the students prepare a 5-minute kind of presentation come informal discussion in which they can discuss a topic of their choice in some detail, and then the interviewer can ask questions about the topic that they've prepared. And then in most interviews also the lecturer, the interviewer will ask the student to discuss kind of an unseen generic scientific question that's related to the subject area that they're applying for. So, but these would normally be very generic questions that the student would have learned about just from watching things like the news. So, for example, in geophysics, I often ask questions about what the student knows about volcanic activity and earthquake activity around the planet. So it's nothing that the student would have had to have done any specific research to be able to answer. It's just sort of knowledge that they have likely to have acquired through their life. But the interview is very much an informal process. It's not designed to be stressful. It's designed for us to gauge the level of interest of the student, and also for the student to ask us any information they want to know.
Simon, do you want to say from your perspective?
I think you covered it very well there, actually. And I think I would say two things to add to that. I think, first of all, the unseen question. It sounds like it's a sort of an exam question. We don't expect you to know everything. If you did, there's no point in coming and doing your degree here, or anywhere for that matter. You should be teaching it. What we're looking for is the way in which you tackle a question and how you approach it. And you may not come up, there may not even be a right answer to some of these questions. They might be very open-ended. And we want to see how you can argue a point and argue a case. And sometimes students can argue perhaps the wrong answer very well. And that's just as likely to get them a place because they've argued the case very well indeed. But we also know you're going to be nervous. And so we're going to try and make you as relaxed as possible. And it's about you finding out if this is the right place for you as well. This is a subject, or these subjects, oceanography, marine biology, geology, geophysics, that you possibly haven't done at A-level. Certainly the marine side you won't have done at A-level or IB. And so it's a chance for you to ask us questions and to find out whether this is the right course for you. Is it what you expect it to be? Does it fulfill your expectations? So the interview process is a two-way thing. We're interviewing you. You're actually interviewing us as well. So, I say the word enjoy and relax. It's not easy, but try and enjoy and relax.
So Amelia was a student that went through this and obviously persuaded us to let you in. What was it like being interviewed?
It was scary to start off with. But actually, it was, like Simon just said, more about finding out about the course and where I'd fit into that and what I'd kind of, bring to the table and where my interest kind of lay. And yeah, it didn't really feel so much as an interview, it was more just discussion. It was quite enjoyable towards the end.
Did you go in nervous to start with?
Oh, yes.
Did you come out relaxed?
I wouldn't say relaxed,
Okay.
but yeah, no, it was a lot more informal than I first thought it would be.
And in your experience, Derek, what's a good, when we ask the students to prepare a 5-minute discussion point, what sort of topics are good for a discussion point in your experience? What sort of things particularly?
I think the most important thing is for the applicant to choose a topic that interests them, because kind of enthusiasm for the, I guess the subject will come through then. So yeah, common things that students choose as topics when applying for geophysics is about sort of the latest volcano that's erupted, or an earthquake that's happened, or many students, especially recently because of the profile of fracking, many students they'll prepare some short little discussion on kind of the relevance of geophysics to monitoring fracking. So they're normally the best thing to choose is something that you're interested in, and common topics are also things that kind of recently appeared in the news as well.
And Millie, do you want to comment on this? As someone with an experience from the other end, having taught A-level students.
Other good topics come from people that have done coursework, maybe in geography or geology, if you've done a small amount of research, or if you're doing an EPQ extended project, you can always talk about that as well, because you should be coming to the end of that process now. But in general, it's something that you enjoy and that you're enthusiastic about, and that hopefully you'd want to go forward and research, because that's really what the interview process is about, is getting to know the department and how it works and who you might be working with in the future. So anything you're keen to talk about is a good start.
Well, that leads us really nicely on to a discussion about EPQ. So we always get questions about this. And so here's a question that I've got here. Is doing an EPQ in a related subject a good idea if I want to apply to Southampton for next year? Is it useful to do an EPQ that relates to my future degree topic? So let's start with Millie, because you know lots about EPQs.
It is a good idea. It's a good idea for a number of reasons. The EPQ gives you a chance to research something that interests you in your own time, and obviously you have a report and a presentation, and that's a really it's a good gateway into degree level education, because you've got a chance to research by yourself and to refine your question. And then developing some presentation skills is a really essential degree skill, and you'll do a lot of that whilst you're here. So it is a good idea to pick something that hopefully overlaps a little bit with your A-level topics and feeds into what you're going on to do your degree in. In part because if you enjoy it and you're interested, you're going to do a lot better. But also it does mean that when you go to university interviews, you've got a pre-made topic that you can talk about in a relevant field. I don't know if you've got anything to add to that.
EPQs are tricky. I'd recommend doing them. If you want to do an EPQ, do it. We don't count the EPQ as such towards the points you need to get into a university course at Southampton. However, when it comes to the sort of grades, when it comes to August, when your A-level grades come in, if you're marginal and you've got a good EPQ, then that EPQ would make me, as an admissions tutor, decide, yeah, okay, if I've got two students, one's done an EPQ, has got a good grade in it, the other one hasn't, and I can only take one of you, I would take the one with EPQ. It also shows you've got a passion for a subject, which is going to help you when it comes to talking about the subject with the interviewer. So it all helps towards getting into university. I would only say one thing. If you are struggling, then focus on the A-levels rather than the EPQ. If you find that things are going well, then there's nothing wrong with doing an EPQ, and it can help. But word of warning, it doesn't count initially towards those points you need to get into university at Southampton. Other universities do vary, but we look at the sort of what grade you get at A-level rather than necessarily your total points.
Derek, do you want to add to that?
Just one thing, we do read the personal statements written by the students in advance of the interview. So if you have done an EPQ in a relevant subject, or even if it's in a completely different subject, if that's mentioned within your personal statement, then it gives us an opportunity to kind of see where your interests lie, and also gives us an opportunity, subject matter to discuss in the interview. So it's just a way to convey your enthusiasm for science, really.
I would say that we'd probably, when it comes to the questioning, we'd probably pick up on the EPQ. So you've actually got something that you probably know more about than we do, having done the EPQ. So there's a surefire way of making sure you excel in that interview.
And Amelia, did you do an EPQ?
The EPQ, I don't even know if it was around when I was at that stage. It certainly wasn't offered to us at school, so I can't really comment too much on it, but it sounds great. So.
And I think the point, I think we said this already, but the point is that a lot of the learning style at university is much more like the EPQ project work. So we assess in a combination of written assignments and giving presentations. And so learning those skills early on while you're actually still at school is going to give you an advantage when you come to university, because it's a lot more similar to university style learning. Okay, so let's move on and talk about A-levels choices then. Now, a lot of you out there will have probably already made your A-level choices, but some of you won't. So I'd like to just have a quick discussion about what are the most ideal A-level subjects to take for the different types of courses we offer. So let's start with marine biology and oceanography, and then we'll move on to geology, geophysics. So marine biology and oceanography.
We love straight sciences. Now, not all of you are doing straight sciences. If we're coming in at the BSc level, we want to see at least 2 sciences there, and they can be from a combination of mathematics, biology, chemistry, physics, geography, geology, environmental studies. If you're looking at one of the, I suppose, higher end courses, particularly if you're looking at, say, masters with study abroad, we would want your A-levels to be in the sciences. So we'd want to see 3 from that combination of maths, physics, chemistry, biology. I've got one somewhere, geology. So, as I said, do always check whenever you go into universities, looking at universities, look on their websites. They will make it very clear what's required. And it's quite frightening how many students turn up or put their applications in, and it's very clear they've not looked at the requirements. Those aren't sort of guidelines, they are strict requirements in what we need. So science, a good science base is what we're looking for. But if one of your A-levels happens to be in history or in English or something, that's fine. You can learn some good essay writing skills from those subjects.
And obviously you need biology from marine biology.
You've got to have biology from marine biology, so I should have said that, yeah.
Do you need maths and physics for oceanography? Or?
No, if you've got, say, biology, chemistry, geography or something, that's fine. I think, if you've got a choice at this stage of deciding, do I do maths or do I do something else, I would say one of the most useful degree of A-levels you can ever do is maths, which is probably not going to be a popular statement for some students, but if you can hack the maths, take it. This could be the most useful A-level you'll ever do if you want to go into any sciences.
So Derek, what about geophysics and then geology more generally?
So for geophysics, the 2 most important subjects are, apologies, are mathematics and physics. And then we do prefer the 3rd A-level subject to be in a science. But if the grades in maths and physics are very strong, we will consider a 3rd subject that's not a science. So the most common case that we deal with is if the 3rd subject is geography. It's doing a combination of maths, physics, and geography is quite a common choice for students that want to do geophysics. But maths and physics are essential. For geology, I think the entrance requirements are similar to oceanography and marine biology, that we require 2 sciences in A-level, preferably 3, but at least 2.
And what about IB? Let's just mention that as well. More and more of our students come in through that route. So to comment on IB choices?
We're very keen on IB. IB gives a good broad education. We are looking again for hires in sciences. So we're looking for hires in a combination of maths, physics, biology, chemistry, geography. So in IB, with A-levels, we're looking at a minimum of an A and 2 Bs for the basic BSc level. When we're looking at IB, we're looking at about 34 points equivalent to get onto the courses. And again, do look at the websites, because they do vary from year to year. But they will give a very clear indication, not only of which A-levels, but also which IB scores we'd like for a particular pathway in the marine sciences.
So since we've got Amelia here, how did you get into oceanography? What was your pathway here?
So I did biology, chemistry, maths A-level, and geography AS. I initially thought I wanted to do biology at university, so my 4 other options for my university choices were all just straight biology courses, and Southampton was the only institute that I applied for oceanography at. I then made the tough decision to put Southampton first, because I decided I actually wanted to do oceanography. And then through my first year, I realized I really didn't like biology at all, and became more and more towards the kind of physical side of oceanography, and then eventually kind of towards almost geophysics, but not quite, sort of on the edge of that. Maths was really important. So depending on what maths level you enter into the university at, depends then on what module course you get put onto for the maths. So as I had done A level, then I was put on the highest kind of maths course in first year, which was has really helped me throughout. And chemistry as well, I think, was a very good choice. And looking back on it, I think I would have changed biology to physics personally, but that's just the route that I've gone down. So I think the 3 sciences has really helped me. But having said that, I think as long as you're strong in the math side of things, then the first year modules are ready to get everyone up to pace. So even if you don't have the biology background or the chemistry background, then they are all kind of started off at a basic level so that everyone gets up to the same level after that first year. That's how I did it. Oh, and I did the 4-year MSci oceanography course, but I think we're talking about the differences between the master's courses. I'll wait for that one.
And I think Amelia said something that's really typical for a lot of our students, which is we have a very flexible pathway through our degree systems. People come in on marine biology degrees, exit on oceanography degrees, come in on geophysics degrees, exit on geology degrees, come in on geology degrees, exit on oceanography degrees. And the first year is very general, and a lot of people, because they haven't studied these subjects before, spend some time working out which ones they really like and which ones they actually have had quite enough of. And that's fine, and that's actually what a lot of us did. So even back in my day, so I started off at Southampton University as a chemist, and I was studying for chemistry BSc, and I was doing subsidiary oceanography. So rather like you, I did the subsidiary course and actually ended up as an oceanographer, and that was again a lot longer ago, but it was absolutely fine to be and the flexibility in the Southampton system allowed me to graduate in a different degree from what I entered on. So Millie, what about you? How did you get to be a PhD student here?
My pathway is a little bit different. My A-levels were geography, geology, archaeology and environmental science. I then did my degree with the Open University in geosciences. I did a master's in Swansea in environmental dynamics and climate change. I took some time out to teach in between. And now I'm in the 2nd year of my PhD looking at ocean circulation and rapid climate change events in the North Atlantic. So slightly different, but it was an interesting path.
And I think that makes another really important point, is that some of our students come straight from school and some of our students come by all sorts of different routes, and we have a wide range of different experiences. So we have mature students, we have school leavers, we have international students, we have UK students, and this breadth and diversity actually is good for everyone's experience, I think.
Yeah, I think one of the questions that was brought up was, do we have many mature students? The answer to that is yes, we do. And as a department, we have a healthy mature student population, and that's mature students from sort of the age of 21 to 51.
And more.
And more, yes. That's true, actually. Yes, it's never too late to study.
Yeah. While we're talking about that different diversity of getting into the degree system, let's talk about the foundation year. So the University of Southampton runs a lot of its engineering and science programs with a foundation year, and so this is an additional year pre-doing the degree, and where you actually focus on acquiring the skills required for your engineering degree or your geophysics degree or your science degree, or in fact they have humanities foundation years as well. And so that's another different route into university study, particularly if you've had a break since leaving school, not actually studied and done examinations for a significant period of time. So it's about spending a year relearning how to learn and how to be assessed and how to operate in the university environment. But it's also specifically for people that perhaps chose the wrong A-level combination for their now chosen career path. So, for example, you may have chosen humanities A-levels, but actually now decided you want to be a scientist. And you might have chosen humanities A-levels and want to be an engineer. You might have chosen biology A-levels and want to be a geophysicist. So the foundation year allows you to repurpose and refocus your skill set, so you're ready for the science degrees. So again, it's not too late. If you're listening to this and you think, I haven't chosen the right things, there are options to get back in at the right level, and that's our foundation year. Should I say anything else about that?
No, it's a well-respected foundation year. It's in-house now. So you are, some foundation years around the country, you're sort of with a college of further education somewhere, and they take you through the foundation year. we brought our foundation years into the university. So you start the student experience from day one, and you are integrated to the university life. So it's if you like, it's a pre-course year. It's giving you that grounding, that basis, which helps you then develop. And these days you are covered by student loans and things to cover that foundation year.
So there's a question here about what qualifications are needed to get onto the foundation programme. So if you're a current A-level student, then the standard offer will be an A and 2 Bs like the other offers, but it'll be in the subjects you have, obviously the ones you've chosen. So if you're a more mature student that's graduated with some A-levels maybe 5, maybe 10 years ago, and you've got some other relevant experience, then obviously that's taken into account during the application process, and there'll be an interview and there'll be some sort of assessment of your aptitude for science study or engineering study now. So it's a bit more of a vague answer, and it depends on whether you're a current A-level student or whether you've got a longer CV and they're bringing other qualifications to the table.
And I think you need to speak to us. I think we have students who perhaps done a few modules in an open university course as a way of getting back into education. And if they're the right courses, we will sometimes take you straight into the degree program. And so, everyone's different, everyone's an individual. And, although we have the basic, I suppose, protocols there for people doing A-levels or who've done their own A-levels or doing IB, we have people from all walks of life coming to join us here to do their degrees. So talk to us, and we'll work out what you need to do to get a place on the degree course.
So let's talk about this difference between the bachelor's and the master's courses, because it's a bit confusing, and we bandy these acronyms around. So we offer 3-year degrees and we offer 4-year degrees, and then we also offer 1-year master's degrees, but we won't talk about those just now. So let's talk about the difference between the 3-year bachelor's degree and the 4-year integrated master's degree. Derek, let's start with you.
So for geology and geophysics, there actually isn't a huge amount of difference between the first 3 years of the MSci program and the BSc, the 3-year BSc program alone. The difference in the MSci program is that you do an additional 1 year at the end, of which a large component is an independent research project. So if you do the MSci program, you end up coming out of the degree with a year's extra taught experience, but then crucially you have evidence of a significant amount of independent research. If you do the BSc program, you do both in geology and geophysics, you do a smaller independent program in the final year of your degree, but it's not as significant, I guess, and amount of work as is required for the thesis for the MSci program. Kind of the choice of BSc or MSci, it very much depends on the interests and requirements of the applicant. Many students who are very, very good will settle for the BSc degree, especially if they want to then go on to another university or stay in Southampton to do a 1-year specialist master's degree. Many also will get a place, they'll get a job offer or a PhD offer after 3 years. The advantage of the MSci program is that in general, it does make you more employable, because most companies and other universities, they recognize that the level, especially reached in research, is higher when you come out from the MSci program. But it's very much a case of choosing the length of program that suits your requirements.
Simon, do you want to talk about that?
Yeah, I would say don't worry about it. Generally speaking, if you want to go on to do a PhD, you must have a 4-year program or a postgraduate publication, so a master's of some sort these days. Certainly if you want to go and study abroad, they will expect you to have done 4 years prior learning and training before you start a PhD. So certainly if you're going down the research route, I would recommend looking at the master's or doing the BSc with a 4th year to do a specialised MSc. Some companies are happy with just the BSc, and obviously if you're using your degree as a stepping stone to, say, accountancy or business, and many students do, about 30% of our students go on to do other things like teaching, accountancy, and so on. And in that sort of situation, you really probably want to focus on the BSc, and then your 4th year will be doing, well, starting your accountancy exams or doing your teacher training. But don't worry about it. You don't have to make your mind up once you're here until the end of the 2nd year. The first 2 years are identical in the marine science pathways. And it's only the third year it starts to sort of diverge a bit. And so you've got 2 years to try the subject before you finally commit. And I've had students, tutees, who change their mind about 3 or 4 times during their first 2 years. You know, if they've had a good week, they're saying, right, I'm going to go through and do oceanography for the rest of my life. And they get a bad week and they say, I've changed my mind, I want to go and become an accountant. Usually they end up doing the 4-year program, I hasten to add. But you can change, and it's not worth losing sleep over. It goes with any degree course. Many universities offer degree courses with 3 or 4-year options these days. And they're going to be very happy, usually, if you to switch at any stage in those first 2 years.
So Amelia, you did the 4-year degree, didn't you? Did you come in on that, or was that at a later stage?
I came in straight into the what was called M-Ocean at the time. It's now called M-Sci, so Masters in Science. I decided to do this personally because of funding. So back when I applied, you were able to get a student loan for the undergraduate program, so the 3-year program and also the 4-year program, but you weren't able to get funding for a separate master's. And I knew I wanted to do a master's. So in order to get the funding for a master's, then I had to do the 4-year combined option. I don't know if this is now the same.
It is.
Yeah. It's the same and more difficult, actually,
Yeah.
because this, the fees are now £9,000 when you came in.
Yeah, really, yeah.
So that is something to bear in mind. If you apply for the 4-year degree, your student loan will cover those 4 years of study. Whereas if you graduate with a BSc and do a standalone master's, you have to apply for graduate loan to pay for that 1 year, and you need to weigh these things up.
And certainly the days, in days of yore, there used to be things called grants for postgraduate study, and they even provided support for living. They don't exist anymore. So you do have to think about how you're going to fund your master's research.
Melanie, do you want to say anything?
I mean, mine is separate. So obviously, my master's was just a 1-year standalone program, and funding is really the key consideration there. And particularly if you want to go on and do a PhD, you do need a master's. And doing one of the 4-year programs is it's a very sensible way of getting an M.Sci or an M.Job. And I mean, it's a fantastic course. You get to really choose your research project on the M.Job, and we've got master's students working with PhD students at the moment on really sort of current research. So it can be quite exciting in terms of guiding your career where you want to go.
And I think it's important to emphasise that, within Ocean Earth Science here, the research projects aren't sort of projects we have on the shelf, which are sort of labelled project number 1, 2, 3, and we bring them out every year. You're actually working with a research team doing frontline research, and you are part of that research package. And so you're working alongside people who are at the forefront of their field, and you are learning how to do research. And it's quite exciting.
Yeah. I mean, we have master's students working on our projects at the moment, and the aim is for them to get a publication at the end of it. So particularly if you're looking to go on to research to get your master's work published is a particularly big help. And we do encourage them to push towards that.
So we've talked a lot about doing degrees to go into research, because that's obviously what we've all done. I want to talk more generally, though, about general employment of our graduates, because obviously a really significant proportion of our graduates go out there and get jobs and have fantastic careers. And we need to just explore a bit about what the differences are between geology and geophysics, marine biology and oceanography. So should we start with geology and geophysics? And geophysics is at the moment fantastic employment.
So the last couple of years, as far as we know and can track students down, 100% of the students that exit with either the BSc or the M.Sci geophysics, they find a job or further postgraduate study in geophysics within 6 months of completion. For the geology degree, the stats are still very good. They're slightly lower. It's something like between 90 and 95% of the BSc and M.Sci students will find employment for further study within 6 months. So in general, both the geology and geophysics degrees make you highly employable and also train you for further postgraduate study.
So what sort of companies are they going to? Can we just get a flavour?
Most of the geophysicists and geologists will work for either oil companies or a big employer such as Shell, Schlumberger, BP. In the UK, especially in the south of England, there are many consultancy companies to the petroleum industry, so smaller companies that do particular contract work for larger companies, and that's a common destination for many of the students. Students also will work for environmental assessment companies. Most of these companies, they'll do geological and geophysical assessments of sites used for construction or for major infrastructure projects as well. Those are probably the most common kind of career destinations. Many students do go into things like accountancy and finance as well. The geologists, and especially the geophysicists, are highly numerate, so they can retrain quite easily to do any subject area that requires good math skills.
And I think the other thing that I notice is that the employment market is global. So our students are getting jobs in Australia, in South Africa, America. They're popping up all over the place.
Mm-hmm.
And they do keep in touch. And that's one of the really powerful things, is to keep in touch with our alumni and get them to come back and talk to current students. So it is a global marketplace, especially in geology and geophysics.
And especially now in the modern day and age, geophysicists and good geologists are highly in demand, because generically oil price is very high, the price of minerals are scarce, and the price is high. So companies are prepared to pay large salaries, especially if you move abroad. So for example, a few years ago, one of our geologists went to work in the Middle East and was paid in excess of £100,000 a year, tax-free. So the salaries that you can earn in geology and geophysics can match those that you can get by working in the city in finance.
Millie, did you want to say something?
Yeah, we have a lot of case studies for geology and geophysics, and where people go after their degree on the geology Facebook page, which there's a link to on our blog for the MOOC. But it follows up on students and where they've been a couple of years and sort of 10, 15 years after they've left, which is quite interesting if you'd like to read more.
So we've got 5 minutes left. So let's talk about marine biology and oceanography and career destinations, again, beyond research.
If we look at the 6 months after graduating figures, they sound slightly lower than the perfect figures for geophysics. Between about 85 and 90% of our students have jobs in the first 6 months. That's biased a little bit because marine biology in particular does attract a lot of people who are enthusiastic surfers and skiers. And so quite a high proportion, usually about half a dozen students every year, will take a year out before they start looking for jobs or doing PhDs. And so they go off and they become volunteers, and that doesn't count towards the employment record, or they go and teach surfing as a common thing. And then they come back. We usually get lots of emails and things around about May time when they start thinking about their next job, and they get jobs. Where do they work? It's one of those questions people ask because they think, well, what do oceanographers and marine biologists do? All of the big energy companies and oil companies employ oceanographers and marine biologists. It's not just about finding the oil and the gas, it's also about looking at the environment in which they're finding it, trying to work out the waves that are going to hit their rigs, the environmental conditions that are going to affect their operations, and the impact those operations have if there's an accident or a spill. And that involves marine biologists, it involves oceanographers. And the big companies like Shell, BP have environmental divisions or oceanographic divisions. In fact, one of my ex-students is now head of Shell's environmental impact team worldwide. The Environment Agency employ large numbers of oceanographers and marine biologists. They monitor our coastlines and have a requirement to do that, as do things like the fisheries people. So fisheries employ large numbers through government. All of the construction companies, people like Halcro, Costang, have oceanographic divisions. Again, they need to know what waves are going to hit our structures. They need to have some understanding what's going to grow on the structures and affect their structures, how those structures will impact the environment. And so they have, again, entire teams. And then there's consultancy. One of the biggest consultants in the world, Fugro, employs something like 6,000 scientists. About 1,000 of those are actually in sort of the marine field. So there is a huge wealth of opportunity out there, commercial work, government work, as well as research. And certainly on the oceanography side, there's a huge demand. We're not producing enough oceanographers to meet that demand today. So if you are thinking, if you are numerate, if you have maths, physics, chemistry interests, then you're going to be in very strong demand. We can't offer quite the same salaries as they get in geology. I'm thinking about changing my degree for part-time. But the salaries are generally good. They're comfortable. You will never be a multimillionaire as a scientist unless you end up sort of a Steve Jobs type person. But you will never be poor. And
What
never
about,
bored,
what about
never
your
bored.
friends? What about your cohort you graduated with? What do they do?
So I have one friend who's become an ROV pilot for food grow over in Southeast Asia. I have a friend who's working for the Natural History Museum in London. Friend who's working more locally, again, for a sort of oil consultancy type company. Friends who are working for oil spill response. So if there's an oil spill somewhere in the world, then they go out and sort of mop it up, or they model where the oil is going to go. So they do some kind of in-house modeling as well. That's about all I can think of off the top of my head. But
That's great.
it's a really kind of broad spectrum.
We started off talking about energy, and actually one of the biggest, fastest growing areas of our industry today is renewables, offshore energy, whether it's tide, whether it's waves, whether it's wind, a workplace environment, and they're recruiting at a phenomenal rate at the moment, and that'll go on for the future decades.
Okay, so I'm going to wrap this up now because we've been on air for nearly an hour. I just want to answer one more question that's quite relevant, which is when is the next open day? So we have open days 4 times a year, where you're welcome to come and see the university, come and look around the Oceanography Centre, come and talk to admissions tutors and students and staff. And we run these in July and in September. So the next open days will be at the beginning of July for 2 days in 2015. And again, the details will be on our website, and then there'll be a further 2 open days in September 2015.
And if you can't make those open days, contact us, talk to us. If we can, we'll try and show you around. But try and make the open days because you'll see the department in full flow.
So thank you for joining us for this Google Hangout. We'll be doing it again in 2 weeks' time, and we welcome you back there then with some more questions. Okay, so goodbye from all of us.
Bye.